Hello, IG2 Extended Math students. We're going to look at this problem, linear programming problem, that we worked in class on a Nearpod. Here is the problem. It's a paper 4 question from 2017. Bernie buys X packets of seeds and Y plants for his garden. We've assigned our variables, and he wants to buy more packets of seeds than plants. So that's reflected in our first inequality, X is greater than Y, more packets of seeds than plants. Now we have a couple other inequalities that we need to write to answer question A here. He also wants to buy less than 10 packets of seeds. So that's X, our variable, and 10 is our constraint. So that is X is less than 10. Not 10, but less than 10. And again, we know those are going to be natural values, 9, 8, 7, etc. Okay, then we have at least 2 plants. So it could be 2 plants, but it's going to be greater than or equal to 2 plants. Okay, we got 2 constraints that we'll be able to graph. Now we're going to look at a third constraint that his maximum cost can be $21. Each packet of seeds cost $1. That's X. 1 times X is X. That's the cost for seeds. Number of packets is X times 1. That'll just be X. So I'm going to add the cost for the plants, $3 per plant, times the number of plants, 3Ys. And our inequality, should have written over here in the answer box, is less than or equal to 21. So he can spend $21. Might be nice, though, that he saves some money for something else. All right, let's go to the graph. We're going to graph these inequalities. Oh, one of them has already been graphed for us. We got a little strange scale here. I wanted to point out that we've used a different scale on the x-axis than on the y-axis. So you can see that our boundary line that we're going to draw is not at the expected angle we would like to see because of the scale. Actually, we do like to see it, and you'll see why. Where is it? X. Line, boundary line. So we this is y equals x is the boundary line. But of course the equality is something else. The inequality is something else. It's got a I wrote it backwards, but x is actually more than y was what they told us before. X was more than y. So that's the inequality, but I need to draw the boundary line, so I made it an equation. Okay. Now the next one that we have to draw is x is less than 10. Our last constraint, sorry, not our last constraint, next constraint, y is greater than or equal to 2. And finally, we have our cost, maximum cost constraint, 3y less than or equal to 21. We need to graph the boundary lines, replacing basically the inequalities with the equalities, and try and graph each of these functions. Okay, well, x equals 10 is our boundary line. Our boundary line is going to be dashed like this one is because it's an inequality, it's less than. Okay, so I'm going to start a vertical line at 10 if I can find it on the horizontal scale there. Maybe if I move it up a little bit I can see it. Okay, so I need a vertical line at x equals 10, and it's going to be dashed. So that's one of our constraints. Okay, and then the next constraint is y is greater than or equal to 2. That's going to be a continuous line, solid line, right? Dashed line, solid line, and then another solid line on our cost constraint. We need to find some way of plotting this equation. If I make it an equation, can we figure out a way of plotting it? Well, to me, the easiest method is to use intercepts. Okay, so the y-intercept is when x is equal to 0. Solve this equation for when x is equal to 0. 3y equals 21. Y is equal to 7. That is the y-intercept. The x-intercept is going to be when y is equal to 0. So now y is equal to 0. This term disappears, and I see that x is equal to 21 if I'm plotting the boundary line. Okay, so I have to plot those points to plot that line. I chose black here, so 21, 0. 21, 0. Oh, it's down here, not up there. Okay, there is 21, 0. And then 0, 7 is up here. And I want to connect those, hopefully with a straight edge, something that'll make it evident that it's a straight line and not something else. All right, solid. That's okay because it's an equal sign on there, less than or equal to. Now we want to shade the regions that are opposite all of these lines. First line. Let's take the test point 5, 0. Excuse me, 0, 5. Or I could have taken 5, 0. I can test either point. Okay, if I put in 5 for y, is that greater than or less than x? 5 for y, 0 for x. Oh, that's greater than. So our inequality is not true. So our guidance is again to shade the area that's not true. So we want to shade basically above this line. Okay, that boundary line. The next boundary line, x is less than 10. That is to the left of that line. That's where x is less. So we're going to shade where x is greater than, not the solution. And then our y is greater than or equal to 2. We're going to shade under that line. Okay. We still have some kind of conflict in this region here. We need to figure out which part of this to shade. Okay, so look at our inequality. Maybe I need another test point here. How about 8, 6. So 8, 6. 8, 6. That's 8 plus 18, 26. It's less than, it's not true. That's where we want to shade, where it's not true. So I'm going to shade above our cost line. So something's missing here. Oh yeah, this little bit in here. Yeah, so our region is of solution is all the points in here. Okay, and I can't buy any whole plants. Excuse me, I can't buy any half plants, or half packets of seeds. So really, I'm limited to all these intersections of coordinates for my possible solutions, however many that may be. Okay, the next question was, look at 8 packets of seeds, and I go up, and I'm still below 4. Oh, it's 4.5 anyway, so 4 is the maximum number of plants he can buy based on the cost. Okay, so he can buy 4 plants. Find the maximum number of, Bernie buys 8 packets of seeds. Find the maximum number of plants he can buy. Okay, well, if we went back to our graph and we looked up here, I don't know how it's going to connect on the video, but we're going to go back. Four plants. And finally, find the total cost. Well, remember our cost function is 3x plus 3y. So that's 8 packets of seeds plus 4 plants. Sorry, 3 times 4 plants. I think the answer is $20. Oh, that's less than $21, so it seems like a reasonable answer. Okay, so final thing I would like to add, at least on this problem, was an optimization problem. Can we optimize cost? Can we optimize cost? So I graphed it another way on Desmos.com. Nice graphing site. I had to actually use the opposite symbology for the not solution, basically to shade the appropriate areas. And so again, you have your region in here, and we're going to look at the cost function, which was less than 21. This was the cost function. So normally, or sometimes I should say, you're going to have to do some optimization. So you may want to maximize the cost. How do you maximize the cost normally in these things? You look at the corners. You look at the corners and see where the maximum cost is. Well, I only have 2 corners to check actually here. We spent 20 elsewhere. How much are we spending at these? Oh, we have to check. We do have to check these. Sorry, we have to check all the vertices. Okay, so I didn't quite make it to those vertices, but they're going to be $21 for both of those 2. So somewhere near those vertices, we know that's the $21. That's the maximum we can spend. So somewhere along here, this point, this point, this point, we're going to figure out the maximum cost. And in fact, we already found our answer. It was that point, 8 packets of seeds and 4 plants. $20 is the most we can spend. I think I might correct myself. Does that intersect? 9 packets of seeds and 4 plants. 9 plus 3 times 4. Yes, indeedy, we can spend $21. Thank you. Okay, a quick review of linear programming. What were our steps? How did we accomplish it? Section 5-6. One, write your inequality. 2, inequalities. 2, graph your boundary lines. you have to decide whether they're dashed or continuous. You have to decide. Again, if it's greater than or less than or equal to, equal to, that is a solid line. Okay? If it's less than or greater than, it's a dashed line. Shade the area that's not solution, which again we can use a test point to help us with that. And then finally we want to answer the question, optimization perhaps. Look at your solutions, use your solutions, maybe the vertices, the corners, to optimize. That's it.